September 14, 1943. Cold morning fog over the naval testing grounds at Portland, England. Lieutenant Commander Samuel Morrison stands on a dock, watching a recovery crew haul up a defensive mine from the harbor floor. The mine is intact, perfectly positioned, but utterly useless. Morrison knows what the divers will find inside: corroded contacts, salt-eaten wiring, a detonator that stopped working weeks ago. He is a naval ordnance specialist, and he has just confirmed that the Atlantic's defensive mine network is collapsing in silence. Morrison's assignment is technical oversight of Allied mine deployment across convoy routes. For months, intelligence reports have shown U-boats operating with disturbing confidence in waters supposedly protected by defensive minefields. Submarine commanders are navigating channels that should be death traps. Morrison suspects the mines themselves. Standard procedure assumes mines remain active for their rated lifespan. Morrison orders systematic recovery and inspection of deployed units. The results are catastrophic. Of 38 mines pulled from active fields, only 12 show functional detonators. The rest are corroded hulks. Salt water has penetrated the housings, eating through contacts and shorting electrical systems. The Atlantic's defensive barrier exists only on planning maps. The scale of the failure is immense. Thousands of mines lie dormant across convoy approaches, coastal choke points, and harbor defenses. U-boats are slipping through gaps that commanders believe are sealed. Morrison calculates the operational impact. If the failure rate holds across all deployed fields, roughly 68% of Allied defensive mines are inert. The convoy system depends on channeling submarines into predictable routes where escort groups can engage them. Without functional minefields, U-boats have freedom of movement. Morrison submits his findings to Naval Command with a stark assessment. The mine network must be rebuilt, or the convoy system will collapse under increased submarine pressure. Naval Command assigns Morrison to solve the problem. He has 4 months. The challenge is not just technical but logistical. Existing mine designs use standard waterproof housings that fail under prolonged salt water exposure. Rubber seals degrade. Metal contacts corrode. Electrical connections short out. Morrison needs a detonator system that can survive months submerged in seawater while remaining sensitive enough to trigger on contact. He begins with materials. Standard rubber seals are inadequate. Morrison contacts industrial suppliers and identifies vulcanized rubber compounds used in deep-sea cable insulation. The material resists salt degradation and maintains elasticity under pressure. He orders sample housings fabricated to tighter tolerances than standard naval specifications. The detonator contacts present a harder problem. Existing designs use brass or copper alloys that corrode rapidly in salt water. Morrison reviews metallurgical reports and identifies a corrosion-resistant alloy developed for marine applications, a nickel-chromium compound with proven resistance to chloride exposure. The alloy is expensive and difficult to machine, but it does not corrode. Morrison designs new contact assemblies using the alloy, paired with sealed relay switches that isolate electrical components from seawater intrusion. The design is more complex than standard detonators, but it addresses the root cause of failure. Morrison submits the specifications to the Naval Research Facility at Portsmouth for prototype fabrication. The first prototypes arrive in early October. Morrison conducts accelerated testing, submerging units in saltwater tanks and monitoring performance over weeks. Standard detonators fail within 10 days. Morrison's design remains functional after 30 days of continuous immersion. The vulcanized rubber housings hold their seals. The alloy contacts show no corrosion. The relay switches operate reliably. Morrison has a working solution, but now faces the harder challenge: implementation. The new design requires retooling production lines, retraining mine-laying crews, and replacing thousands of deployed units. Morrison calculates the logistics. 42 naval bases across the Atlantic Theater handle mine deployment. Each base must receive new equipment, technical manuals, and hands-on training. Civilian rubber plants must convert production lines to military specifications. Metal fabrication facilities must tool up for alloy contact production. The timeline is brutal. Morrison begins with production. He identifies 3 civilian rubber plants in England with capacity to produce vulcanized housings at scale. The plants are already operating at wartime capacity, producing everything from vehicle tires to aircraft seals. Morrison negotiates priority access, arguing that mine effectiveness directly impacts convoy survival rates. The plants agree to convert 1 production line each to military specifications. Morrison provides technical drawings and quality control standards. The first housings roll off the line in late October. They meet specifications, but production rates are slower than needed. Morrison assigns naval inspectors to each plant to identify bottlenecks. The issue is curing time. Vulcanized rubber requires precise temperature and pressure cycles. Morrison authorizes overtime shifts and additional curing equipment. Production rates increase. Alloy contact fabrication is more difficult. The nickel-chromium compound is hard to machine and requires specialized tooling. Only 2 facilities in England have the equipment and expertise. Morrison visits both, walking production floors and reviewing manufacturing processes. The facilities are small, precision operations accustomed to low-volume work. Morrison needs high-volume output. He brings in naval engineers to redesign the machining process, simplifying steps without compromising quality. The facilities resist. Their reputation depends on precision. Morrison shows them corroded contacts from failed mines and explains the operational consequences. The facilities agree to scale up. By mid-November, contact production reaches the required rate. Morrison now faces the human challenge: retraining mine-laying crews. Standard procedure for mine deployment is straightforward. Crews load mines, set depth and activation parameters, and deploy them over the side. Morrison's new detonators require additional steps. Crews must verify seal integrity before deployment, conduct electrical continuity tests, and document serial numbers for tracking. The process takes longer and requires more attention to detail. Morrison develops training protocols and deploys instructor teams to each naval base. The teams conduct hands-on sessions, walking crews through the new procedures step by step. Resistance is immediate. Crews are overworked and skeptical of changes that slow deployment. Morrison addresses the skepticism directly. He brings corroded detonators to training sessions and explains the failure rates. He shows crews the testing data. He makes the case that 10 minutes of pre-deployment checks prevents months of wasted effort. The message lands. Crews adopt the new protocols. By December, production and training are synchronized. New mines with Morrison's detonators begin deploying across Atlantic convoy routes. Morrison implements a tracking system, logging every mine by serial number, deployment location, and date. The system allows pattern analysis if failures occur. Morrison also institutes random recovery and inspection protocols. Every month, a percentage of deployed mines are pulled up and tested. The data will show whether the new design holds up under operational conditions. Morrison knows the program's success depends on sustained performance, not just initial results. The first operational data arrives in early January 1944. Recovery teams pull up mines deployed in November and December. Morrison reviews the inspection reports. Of 26 recovered units, 24 show full functionality. The vulcanized housings remain sealed. The alloy contacts show no corrosion. The electrical systems operate correctly. The failure rate is 8%, down from 68%. Morrison cross-references the data with U-boat activity reports. Submarine sightings in mined waters have dropped sharply. U-boat commanders are avoiding areas they previously transited with confidence. The defensive barrier is working again. Morrison expands the tracking system, collecting data from all Atlantic bases. By late January, the pattern is clear. Mines with the new detonators maintain a 91% effectiveness rate over 3 months of deployment. The improvement is dramatic and measurable. Morrison's innovation has restored the defensive mine network. The operational impact follows quickly. U-boats, unable to navigate through mined coastal waters, are forced into deeper Atlantic routes where Allied hunter-killer groups patrol. Submarine losses increase. Convoy losses decrease. The shift is not attributed to any single factor in official reports, but Morrison knows the connection. The silent barrier beneath the waves is functioning again. The program's success brings new demands. Naval Command orders Morrison's detonator design, adopted as the standard for all Allied mine production. Civilian plants across England and the United States begin converting production lines. Morrison's training protocols become mandatory for all mine-laying operations. The innovation spreads beyond the Atlantic. Pacific Theater commands request the new detonators for operations against Japanese shipping. Morrison's solution to a localized corrosion problem becomes a global standard. He receives commendation from Naval Command, but the recognition is quiet. The program's effectiveness depends on secrecy. U-boat commanders must not know why mined waters have become lethal again. Morrison continues overseeing the program through the spring of 1944. He refines the tracking system, analyzes failure patterns, and implements incremental improvements. The work is technical and unglamorous, but the results are measurable. By May, over 12,000 mines with the new detonators are deployed across Allied convoy routes. The effectiveness rate holds at 91%. Morrison's innovation has turned coastal waters into reliable barriers, channeling enemy submarines into zones where Allied forces hold the advantage. The impact on convoy survival rates is significant but unquantified in public records. The mine program remains classified. After the war, Morrison's work receives limited recognition. The technical details of the detonator design are declassified in the 1950s, but the operational impact remains obscure. Naval historians note the improved mine effectiveness rates in 1944, but rarely connect them to Morrison's engineering work. The story is buried in technical reports and logistics summaries. Morrison returns to civilian life, working as an industrial engineer. He does not speak publicly about his wartime service. The innovation that helped secure Atlantic convoy routes remains known only to specialists. The mines Morrison redesigned were eventually replaced by more advanced systems, but the principles he established endured. Waterproof encapsulation, corrosion-resistant materials, and systematic pre-deployment testing became standard practice in naval ordnance. The lesson was simple. Defensive systems fail not from enemy action but from environmental degradation. Morrison understood that technical reliability is a tactical advantage. His solution was not a weapon, but a method, a way of ensuring that existing defenses performed as intended. The impact was silent and cumulative, measured not in explosions but in U-boats that turned away from waters they could no longer safely navigate. Morrison's work did not win battles, but it shaped the conditions under which battles were fought. The Atlantic's defensive barrier, held because one engineer refused to accept that salt water made it obsolete.